Hello, everyone. So, welcome to the UXL Language SIG meeting. So, very happy that today we have Yury Plyakhin from Intel. So, Yury is a senior staff compiler engineer at Intel. He's working on SYCL and DPC++, compiler and runtime. He leads the SYCL Offloading Toolchain and at least the toolchain upstreaming effort in LLVM Clang, and has been contributing to different part of SYCL implementation for several years. So we are very happy to have you, Yuri, today. Thank you very much for accepting. And so please go ahead, and we are very eager to know about your work.
Okay, yeah. Hi everyone. So yeah, today I'll present what we do for upstreaming SYCL offloading toolchain to LLVM. And in this talk, I'll cover existing Clang offload tool, model. And then I'll present what we do for SYCL specifically, like how we change or extend this model. And this talk doesn't cover anything about Clang frontend or driver or SYCL runtime and liboffload. So I'll focus only on offloading toolchain. Okay, so let's start from existing Clang offload model without SYCL yet. Clang offload model is a unified device linking model which is currently used for all offloading compilation in the main branch of LLVM. And key features of it is it allows device-side link time optimization support. It enables relocatable linking for shipping static libraries with embedded device code. And it allows relocatable device code for, yeah. And for that, it introduced Clang linker wrapper. It's a tool which orchestrates all device linking, and it wraps host linker and then does everything that is needed for device. And I'll cover details in the next slides. For device code, offloading model is using a float binary format, which I'll also cover in detail. And when we are doing our SYCL toolchain upstreaming, our goal is to adopt this Clang offload model. So we are trying to fit into it as smooth as possible, but we still need to introduce some extensions. And yeah, let's start from Clang offload model, compilation linking flow. So we start from, for example, couple input C++ files, which both contain host code and device code. And for it, Clang frontend is run for host and for device separately, and is producing host IR object and device IR object per device arc. And then it all put together into output object file, which contains both host code and device images packed into LLVM offloading section of ELF format. And then it all goes for linking to Clang linker wrapper, which, as I said before, wraps host linker. And it does a set of steps, which I'll cover later, and is producing device code, which is ready for host linker to just embed into output binary. So yeah, Clang linker wrapper eventually is calling host linker, and it links together device code prepared by Clang linker wrapper with host code, which is produced by compilation stage, and it all got into final executable or shared library. Okay. So before I provide details about what Clang linker wrapper actually does, I wanted to show like how offload binary looks like, because it will be important for later stages. So offload binary version 1 format is pretty simple. It has header with metadata, and it provides like size for entire binary and also offset to the entry, which contains metadata for the device image and entry size. So it allows to read entry, and then entry contains additional metadata about device image, and also it can keep like key value pairs, like a set of string entries where you can add even more metadata in a free format, and then offset to the image, which is anything you want to put there. It can be like text formats, it can be binary formats, or it can be SPIR-V, ELF, PTX, whatever you need. So basically, offload binary allows you to pack together image in any supported format with a set of metadata, and tools know how to read it and how to parse it. So what Clang linker wrapper is doing? It scans input files for LLVM offloading sections where device code was injected after compilation stage in offload binary format. Then it extracts offload binary entries, because there can be multiple offload binary files embedded there. It groups these entries by programming model, by triple, by arc, because depending on programming model and arc and triple, different like workflows may need to be run. Then it links device code per target, for example, per triple and arc, and then it bundles device code per programming model, because for different programming models, different wrapping needs to be done, because different programming models often use different runtimes. So it bundles device code into bundles per programming model, but now it is multi-target binary after the previous stage. And then it traps bundled image with runtime registration code. And then it calls host linker with host objects and as an input, and with this wrapped image as an input. And host linker links everything together into final binary. So this is vanilla Clang linker wrapper based workflow without SYCL additions. So now what SYCL does? We modify this workflow in several places. On a stage where grouping happens by programming model, we detect that the programming model is SYCL, and then we modify workflow a bit in several places to provide what's needed for SYCL. So for linking device code, we are calling Clang SYCL linker. So basically, linking device code for linking of device code, Clang linker wrapper is calling Clang++. which is then further calling other tools like LDD or something else. But for SYCL specifically, we introduce the SYCL link flag, and we are calling Clang SYCL linker, which we also introduced. And it runs a few steps which are necessary for SYCL. Some of them are module splitter and property sets generation, and I'll cover it also later in details. Then it produces a float binary version 2 format, which I'll also cover later, which we introduced as an extension to offload binary version 1. And then bundling per programming model is passed through for SYCL because Clang SYCL linker already is producing a single bundle inside the float binary, like with whatever targets we have, everything is already bundled into a single float binary. So Clang linker wrapper doesn't need to bundle anything for SYCL. And then the only additional step we do for a float binary is we wrap this image with runtime registration code that SYCL runtime can consume. So what was upstreamed is Clang SYCL linker, integration of it with linker wrapper, device code splitting and property sets, but we just upstreamed infrastructure classes, which can do that, but we did not yet integrated it inside Clang SYCL linker. That's why color of these 3 blocks is a bit different, because this work is not yet complete. It's in progress. And also we implemented this offload binary version 2 format and wrapping of it for SYCL runtime. So what Clang SYCL linker is doing? It gets, for example, several bitcode files. This is device code. For example, it all targets some architecture. So it merges everything together into a single merge module. Also, it links in necessary device libraries, if any is necessary, and of course it links in only reference symbols, not entire device libraries. And then this merge model goes to module splitter, which splits this module per requirements. I'll cover it later. So as an output of module splitter, we are getting, for example, 2 output bit codes, and then each for each of them we also then extract properties which will be needed by SYCL runtime. Then currently we are calling SPIR-V backend to produce SPIR-V out of each bit code, but actually any backend can be used. So basically, yeah, anyone can extend Clang SYCL linker to call different backends to produce different target code. It just currently in our implementation we are calling SPIR-V backend. And also we built a symbol table for the symbols which we want to expose from each module. So if ahead of time compilation is needed, then SPIR-V output is going into some device specific ahead of time compiler. For example, it can be a o'clock for Intel GPU or something else. And then everything like is packed into a float binary, like properties, binary in some form is like ahead of time compiled to SPIR-V, symbol table. Yeah. So what I did not cover, I think I covered here everything. Yeah, and this is example of invocation, like how you can call Clang SYCL linker via Clang driver to link, for example, these three input BC bitcode files. Okay, so let's stop on device code splitting, like why it's needed and what it actually does. We have like two extremes. For example, we can place all kernels into one module. So what it means? It means that common functions are shared. So in the end, you get smaller offload code. And at the same time, if you're using just-in-time workflow, entire module is being compiled on the first kernel submit. It can be good and bad. For the cases where, for example, you're executing just a few kernels out of many, it's wasteful. So yeah, overall, there are some like pros for this mode, but there are some cons as well, depending on your situation. We can also put each kernel in its own module. Cons is it means that common functions used from multiple kernels are duplicated. So in the end, you're getting larger float size. Also, it causes more total just-in-time compilation time because of this duplication. At the same time, you have multiple compiler runs versus one, so you can make it parallel, which can be an improvement for performance. But anyway, overall, it might be bad if you're executing all kernels from this set. So if anyway you are going to execute all kernels, it might be beneficial to just compile single big module, and yeah, actually compilation can be parallelized there as well. So when we are doing compilation linking, we can't predict runtime scenario, like what you would prefer, all kernels in one module or each kernel in its own module. So device code splitter allows actually both scenarios and also intermediate scenario where you can compose. Basically, you can like put together all kernels and then split them per module in some specific way that you need, or that is dictated by some additional requirements. Also, device code splitting is enabling optional kernel features, which is part of SYCL 2020 standard. So with device code splitting, you can split kernels by optional features used in kernels. On the right is an example. For example, if you have some kernels which are using FP64 and some kernels which are not using FP64, and like sometimes you want to run your module or your code on architectures which supports FP64 and sometimes which do not support FP64. Module splitting allows you to split kernels per this optional kernel feature, and so you'll get in the end two modules one with kernels with FP64 usage and others without FP64 usage. Though currently internally we are rethinking this design to make it, because it has some complications that we want to avoid. So yeah, here we are rethinking how we are going to implement this. So what was so far upstreamed? Because here I described, like, in general what device code splitting does and why it's useful, but not everything of it is actually in upstream yet. So currently, what we do is we can split module M into parts, and each part will be a subset reachable from an entry point group. For example, if you have module and you split it by some category, like some entry points allocated in one output module, some entry points allocated in another output module, each of modules will contain subset of dependencies reachable from the entry points transitively. And module splitter that we upstreamed currently can split per translation unit or per kernel. So it is using entry point categorizer, which can assign groups. And groups can be, for example, each entry point is a separate group, and then it will split by entry point. Or, for example, all kernels which came from the same translation unit are a single group, and then it will be split in per translation unit. Yeah, so I think it covers what is in upstream now. And yeah, and what's currently missing here is Clang SYCL linker currently doesn't call device code splitting. So currently, Clang SYCL linker just merges all input bit code together into a merged module, links in device libraries, and then goes directly to like SPIRV backend and then to offload binary. So currently it yeah, this different color used to show what's currently either not called at all or it is partially implemented. So module splitter currently is not called from Clang SYCL linker. Oops. Yeah. Okay. Moving on. So what's property sets? We use property sets to communicate information about SYCL binaries to SYCL runtime. Examples are, for example, SYCL 2020 has this feature, specialization constant, which allows you to specialize device code per some parameters, which will be known only during runtime compilation, for example. But you want them to be treated as constant during compile time, which allows more optimizations. For its support, we need to communicate to runtime offsets for complicated specialization constants, which can be like some structures of some more complex data types. It can be information about, for example, removed kernel arguments due to kernel arguments optimization. It can be some metadata, like how to launch kernels, for example, what are iteration space dimensions. It can be a lot of stuff. Below is the link to SYCL binary property sets documentation, which outlines current set of what it can include, like which property sets SYCL can generate in DPC++, not in upstream, and so which property sets can be consumed by SYCL runtime. So what we upstreamed is the property set like registry class with internal structure. So basically, it is a set of key value pairs where key is category of the property set, like it is some name, and the value is the property set itself, which also in turn a key value set of key value pairs like property value, and yeah. So this part, like infrastructure, is upstreamed, and it also supports serialization to JSON. What's not implemented yet is the connection between device code image produced by Clang SYCL linker and property set. So what we need to add is to extract property sets out of device code and save it into offload binary in the way that can be consumed by SYCL runtime. So yeah, this part is not yet implemented. So now, before moving next, I want to cover offload binary version 2 because it's important for the next step. But before I cover it, wanted to give you a flashback, remind what's offload binary version 1. And now, what we added, how we modified it is the following. So, and all modifications were done in the way that it keeps backward compatibility with version 1, so that we did not have to change all tooling, or did not break any compatibility. So offload binary version 1 is still readable by LLVM, and it can read it. But now it produces offload binary version 2 when it serializes binaries. So what we modified is we updated header fields. We introduced it just renaming. So now it's not entry offset, but entries offset. So it assumes multiple entries now. And instead of entry size, we provide entries count. So we can write multiple entries into offload binary v2. And another modification is we updated string entry to also provide value size. It means that values can now be not only null terminated strings, but it can be arbitrary data. As soon as we know the size, we can read it, and then it's up to consumer to interpret it as they want. Also, we introduced a new type of entry. It is marked with flag metadata. It means that such entry doesn't have image assigned. This is used for if you need to put there some global metadata which affects all images written to this binary. And now device image blob actually contains multiple can contain multiple raw device images. Also, if offload binary contains multiple images, so its implementation detail, it's using shared memory buffer to share backend storage. So that we are not duplicating backend storage for each offload binary or for each image read from this format. Yeah, and that allows us to put together all device images produced by Clang linker wrapper, whether it is multiple target architectures or different formats, for example, both SPIR-V and final binary for the same architecture. We now can pack everything into a single offload binary, and yeah, it allows to skip bundling in Clang linker wrapper. So now I want to cover how this wrapping connects to SYCL runtime. So yeah, as we covered in compile time, Clang SYCL linker produced a float binary v2 with all device images, and Clang linker wrapper adds to it runtime registration code, and then calls linker to link with host code. And yeah, as a result, we have host executable, which contains SYCL register and unregistered calls, which get a float binary v2 as an input. And the float binary contains everything that is needed for SYCL runtime. And in runtime, when host executable is run and register and unregistered calls are run during initialization, SYCL runtime has definition for these calls. So they're called, they get a float binary as an input, and then they are performing extracting device images and do whatever is needed, whatever is required. Like either just register all images and kernels, or maybe run just-in-time compilation for device target if it's like SPIR-V, yeah, or whatever is needed. And yeah, I covered SYCL offload wrapping, basically what it does. Okay, and a bit more details, maybe that will help to put together like all these puzzle pieces. So what we used in DPC++ for offload wrapping is the following. In DPC++, we are not using offload binary version 2. We are using our custom SYCL TGT bin description, which basically provides version plus count of binaries or count of images plus images array. And then each image is actually this, again, custom SYCL TGT device image structure, which contains 12 fields per image. It includes like all these property sets, symbol generated, and some other stuff which is needed. And then what is happening is Clang linker wrapper extracts metadata from input bit code, and it extracts image from or multiple images from it extracts image from multiple offload binaries or images, and it repacks all this information to this SYCL TGT device image structures so that SYCL runtime could consume it. And it adds this SYCL register lib and SYCL unregister lib calls, which points to this SYCL TGT bin description. So in runtime, when these calls are called, runtime is getting these pointers, and then it reads this structure, extracts like all images, then read this next structure, extracts all like fields, and then does its job. What happens now in upstream? We simplified this a lot. So currently, Clang SYCL linker produces single offload binary with all data like embedded as is, and this single offload binary contains multiple images with metadata in a format consumable by SYCL runtime. So we are not producing any of this specific structures. We are entirely utilizing the offload binary with all its serialization, deserialization code. So nothing specific to SYCL in the format itself. Though we, of course, when we put metadata inside the offload binary, we put it in some format which SYCL runtime can read. But these are some like very simple pieces, so it doesn't require us to produce some specific like structures, document them, and provide some backward compatibility for them. So metadata is becoming kind of implementation detail. It doesn't need to be exposed externally. So only offload binary is exposed externally. And SYCL register lib and unregister lib calls are now getting binary start to this offload binary and end size. And then they just use offload binary implementation to read it and then get all the data necessary for the next job. Okay. And this is just a list of major patches merged to implement this work that I described. It's not a complete list, but I think everything that was major is listed here. And to summarize, Clang linker wrapper offloading model is being extended in LLVM for SYCL. We introduced Clang SYCL linker, we introduced offload binary version 2, and we introduced module splitter and property sets implementation. It is not yet complete. There's a lot of future work. Currently, like the next point on my list is to continue developing Clang SYCL linker to reach parity with what DPC++ provides. For example, introduce device code splitting to it, support like SYCL 2020 features which are relied on Clang SYCL linker support, introduce property sets extraction. Also, currently, this workflow is not documented in LLVM currently. The offloading model itself, I think, is documented well enough, and offloading design. But SYCL specifics documentation is currently not there, so we need to add that. And we have steady progress towards goal of having SYCL and in LLVM. Okay, I think that's all I wanted to cover, and there are 15 minutes if in case there are questions.
Thank you very much for your presentation. I think it was very, very interesting. And please let me know if you have any questions. I would like to start. So I see support for specialization constant. What does it mean? What happened right now with specialization constant? And why there is a needed for support?
Currently, nothing happens with specialization constant in upstream. We just do not support this feature. But eventually, what we will need to do and what Clang SYCL linker is supposedly will do is we will need to extract specialization constants from like information about them from input device code, and then populate property sets with information for offsets. What I described before. So if for example specialization constant is some structure with multiple fields, SYCL runtime will need to pass this information to device compiler during just-in-time compilation. And so the workflow is the following: Clang SYCL linker is running some passes which extracts information about specialization constant used from input bit code. Then it puts it into property sets specific for specialization constants, and then it's packed into a float binary, and then SYCL runtime, when it reads a float binary, it also reads metadata, including property sets, and if it sees property set related to specialization constants, it knows how to extract it and pass it into like device-specific runtime, for example, liboffload, or some like level 0 plugin or something, so that device runtime knows what to do next with specialization constants.
I see.
Currently, it's not implemented, so it just implements. Also, in case there are no questions,
There is a question from Tom Unerman.
Yeah, Tom.
Not actually a question. I just wanted to say I've been working on the SYCL upstreaming effort for a couple of years now, and all of what the offloading utility is here and the toolchain does has always been kind of black magic to me. I'd heard terms like module splitting and such, but never had a good understanding for what that actually does. So I just want to say thank you for doing this. This has really helped me out to understand better what ends up happening at this low level.
Okay, thank you very much.
Attila, please.
Yes. So
Hi.
hopefully everything works. Thanks a lot for the presentation. I was wondering about possibly asking a very naive question. So I learned a lot about what you guys are doing with this from the presentation, and now I wonder what the medium to long term vision is. So I'm not even sure. With all this upstreaming, how much is envisioned to be upstreamed out of one API? And if we are meant to arrive at a fully functional SYCL compiler just by setting up LLVM, what would be the hoped timescale for such things? So I'm just asking some very naive questions.
Very good question, actually. I think very good two questions. First question is what's kind of the end goal of upstreaming? In the end, we want like people to be able to just take LLVM release and be able to compile SYCL code. That's our end goal, and it can consist of, there is of course this SYCL 2020 standard. So it like end goal in that sense is maybe modified. So we can, for example, target SYCL 2020 conformance, or maybe a next version of standard or something. Or we can also like target some additional functionality that is needed for some other applications. But the end goal anyway is to have functional SYCL in LLVM, which can be used for some real applications, like used in the industry. Second question, I unfortunately cannot provide dates because like a lot of things are changing. So anything that I provide now will be outdated, like probably tomorrow. So yeah, I would avoid providing any dates.
Okay.
If I can interject a little bit, I would say our goal is kind of progressive improvement. So more and more we're upstreaming bits at a time, kind of building from the ground up. So parts of the SYCL specification will become usable earlier than other parts, of course, and then we're prioritizing those based on certain applications that we really want to enable or that are looking for our support. So full conformance might take quite a while before we get there, but an actual usable implementation should come much sooner for much of the SYCL spec.
Okay, thanks a lot.
Andrei, please.
Yeah, slightly continuing Attila's question. So since the upstreaming is progressing quite fast, is there any support metrics for SYCL features and device backends, or are there plans to provide one once the upstream gets to more usable state? That's timeline question. I also have some question about device spacing, but maybe I'll ask it later.
So at this point, there is no matrix for SYCL features supported. Just because currently, like, we are on a stage where you cannot run any application, so we are still moving towards that target. Eventually, when it makes sense, maybe we might provide some metrics so that people know what's supported, what's not supported. As to targeted devices, currently for this implementation, for like getting it kicked off, we are targeting Intel GPUs. Eventually, like as we upstream more, other targets could be considered, like other device vendors or CPU. So we are upstreaming or implementing SYCL and upstream in the way that like could be extendable for, of course, for other targets or for different hardware. I hope I answered your question.
But the different hardware, is it later in the roadmap or not on the roadmap, but like maybe?
I would say we are like splitting our work on some reasonable milestones, and we are not. So our first milestone is to enable SYCL to be usable by real like applications for at least one target. For example, Intel GPU. So we chose an Intel GPU, and we want SYCL to become workable for real application for Intel GPU. As when we close to this stage, we can sit and look at, okay, what should we plan next? And by that time, I think again a lot may change back and forth. So we decided that it doesn't make sense to spend too much time now for planning some longer term targets until we have something usable for at least one target. But again, during implementation, we are still thinking about other targets, and we are not introducing or we try not to introduce anything that would prevent us from enabling other targets later. So we are trying to design this SYCL in the way that is extensible for other targets later.
Yeah, if I can guess at some of the motivation for your question there, Andre, I'm of the point of view that if SYCL is going to be successful in the ecosystem, it will have to have wide architecture and hardware support. Otherwise, users simply won't adopt it if it ends up being a vendor specific technology. So we are very, very interested in making sure that other vendors are able to come along and add to the implementation and extend the hardware support in the future.
Yeah, I mean, especially given that DPC++ works quite well in our experience on NVIDIA and AMD GPUs. Sorry if I'm saying the forbidden words here. And in upstream Clang, we have like OpenMP offload. I'm not sure how well it works, but like to some extent it works. Yeah, but yeah, I think that answers my question. And on a more technical side, about device code splitting, maybe I missed some parts because I'm not that deeply familiar with how it all works. But would that be major change from how things are implemented right now? Because our code relies on device code split per kernel. Otherwise, the JIT compilation time goes through the roof because we have 100 different kernel flavors, but usually use like 100 different kernel flavors in the same translation unit, but usually use only like 4 during single run. So we use split per kernel, and you support it, but I didn't catch if it's like changing in some meaningful way from DPC++, or it will be more or less the same.
So some implementation details definitely changing, but from functionality perspective, yes, we plan to support kernel level splitting.
Yeah, and it will behave more or less the same. Well, thank you.
I don't have like final option names or something because it may depend on feedback from community, but yes, our intention is to upstream this part so that you can provide some option and get output fields split by kernel.
Yeah, great, thank you. All from me.
Okay, yeah, thank you for the questions.
Many questions. So we are coming to an end. Are there more questions? If not, thank you very much. Thank you again for your presentation. It was very, very interesting. A lot of questions, so very engaging. So thanks again. I remind you all that the next Language SIG meeting will be on July 28th, and we will have a presentation about 1TPB. And news will come by mail. So we're trying to have both a presentation by Michael Voss and presentation from the community. Let's see what we'll manage to do. Thank you very much to all of you for attending, and have a nice.
Can I say one thing real quick? It's
Yeah,
Allison.
sure.
I just wanted to tell everyone we're going to have a new website launching soon in the next 2 weeks, probably mid-May. So just look for that, and if you can also promote it on your social if you're interested. But take a look and give us feedback. That's all. Sorry, Biagio.
Great. Thank you very much. Thank you all, and have a nice day.